Let's study together. Let's both fail or he takes again.
Now,
yeah.
at least that is a positive mental attitude. We're going to both fail this together.
I actually did that once.
You failed once?
I failed a retake. I was really embarrassing. I couldn't take it again. And I just had to do the first one. So I got a 70 on the first one, and then I retook it, and I got a 50.
What?
What?
How did you get 20% dumber?
It was the easiest unit, too. It was just like probability, and I somehow got a 50% on it. It was really
Isn't
bad.
probability always 50-50?
What?
Isn't probability always 50-50? Oh, okay. Okay.
Young challenge. Oh, wait. What's that one thing that you said?
You okay?
When he was like yelling out like that one of his said like yellow. No, that's not. I like just said that's not what it was. Okay. When he was like saying like the kid's name, he said like Arrow, and he was like, "What's Arrow?" I don't remember that.
You're saying it to me like I know.
Okay, ladies and gentlemen. Electronic devices away. Take your computers out. Get logged in.
There was a Unit 1 test review?
There was a Unit 1 test review?
You and Mr. Guy need to plan better and not have you guys' tests on the same day.
He's having a quiz
Wait,
today?
this is Unit 1.
Yes.
Why am I in this?
I don't know.
I'm so sorry, guys. I'm so sorry.
Not so
I'm sorry.
What are you on about?
I'm so sorry.
You know why?
Because she didn't charge it?
Good answer. Good answer.
Wow.
So why didn't you charge it?
I don't know. I was thinking about something else. Do you want,
All night
a
long?
charger? Yeah. I have a charger. I'll use it.
Okay.
And you have a
Excellent.
wall.
Wonderful. Well, no, she doesn't have
This
a wall. There's a wall in the room, though. It's not hers.
Well, she's closer to the wall.
Okay. All right. Okay, question of the day today. Do you have any questions before today's quiz? Anything you'd like me to re-explain, go over, summarize for you, things like that? I can't do everything. If you have specific questions, I will, but I'm not going to go back and do a week's worth of stuff in 5 minutes here.
Like reteach it all.
Take mine.
Whoa.
There you go. There's some papers.
Oh
in
my
there.
god.
There you go.
Oh yeah, you take that one back.
Graphing and energy. What does this mean? What is graphing? Can you go over what graphing means?
Sure, I expect you to know what a direct and an inverse relationship look like on a graph. I expect you to know what a constant and a non-constant relationship look like on a graph. I expect you to know what three things every graph has to have, which is labels, units, and a title for them.
Okay. Okay. I forgot the first thing. Two things he said. Inverse.
Inverse means the line is
Direct.
going down on the graph.
Okay.
Direct means the line is going up on the
Because
graph.
it's like inverted
Yeah.
and like yeah.
Yeah.
Like
Okay.
Yeah.
However you need to remember it, that's awesome.
constant.
It's a straight line.
Like it's just straight and then like
Constant is a
like,
straight line, non-constant
okay,
is a curved
it's
line.
fine.
Oh,
I learned
easy.
all this in like
Easy peasy, right?
a unit.
Okay.
A time.
Other questions, ladies and gentlemen?
Oh, I need example.
All right, go to your EISN, ladies and gentlemen. We're going to be talking about heating curve graphs today, and then we'll take our quiz near the end of the hour. So to do that, ladies and gentlemen, you need to get to slide number 37 in your EISN. That's the one that we are on, ladies and gentlemen. And again, we touched on this a little bit yesterday. We touched a little bit on the difference between heat and temperature. And there is a difference between the two, okay? Heat is not how hot something is. Temperature is not how hot something is. There are actual definitions for them. But before we get into defining them, let's take a look at a short video here, ladies and gentlemen. All right. So basically, ladies and gentlemen, that summarizes the difference between heat and temperature. We don't use the term quantity and we don't use the quality of hotness anymore. For heat, the definition is a measure of the sum of kinetic energy and particles of matter. That is what the definition of heat is. Okay? Now, when we talk about sum, what are we talking about doing with the heat? Adding it all up. Adding it all up together. Okay? So each individual particle has a certain amount of heat, and we add that all together. Okay? It depends on the speed of the particles and the number of particles present. That is what heat depends on. How fast the particles are moving and how many of them there are in the bucket. That is how we will get the heat in something. So an object can have a great deal of heat even though it is not at a very high temperature. How?
So there's more.
What do you mean there's more?
More particles.
Okay, it can be a very large object. Okay? Very large object. A very large object, even at low heat, will have or even at low temperature, will have a lot of heat in it. Why? Because there are simply a lot of particles there. And we're summing them all together. Temperature, on the other hand, is a measure of the average kinetic energy in particles of matter. Now, when you talk about average, what does that mean? Yes. So average, it doesn't matter how many particles are there. An average says, I'm going to take all of these and add them up, and I'm going to divide by how many are there, and we're going to find how much energy is in one particle on average. Okay? One particle on average. So, again, that's a measure of the average kinetic energy in the particles of matter. This is the sum, but both of them rely on kinetic energy, right? Well, what does kinetic energy depend on? What two things?
Velocity and mass.
Velocity and mass. Which of those can you not change about a substance?
Mass.
You cannot change the mass. So the only way you can adjust kinetic energy is by making the particles either move faster or slower. However, in heat, it matters how many particles are there. In temperature, it does not. Okay? Temperature does not care how many particles are there because we're finding the average. Temperature still depends on the mass of individual particles, and it depends on the speed. So what do we know about most things in this room right now, ladies and gentlemen, again? What do we know about their heat or their temperature? What do we know about most things in this room?
They're all similar temperature.
Okay, they're all a similar temperature. They're all a similar temperature. This tabletop and this metal can are the same temperature, correct? Which one has more heat? Why?
There's more.
Because there's more particles of it. Okay? Heat is the sum of the kinetic energy. Both of these have the same average kinetic energy. This one, though, there's a lot less mass here. This one, there's a lot more mass here. There's going to be a lot more heat in this tabletop. Okay? Going to be a lot more heat in this tabletop. Okay? So now let's take a look at it. Christian, you need to take out your headphone, please, sir. Thank you. Okay? Now let's take a look at it this way. The air that we are breathing is oxygen and nitrogen, and we talked about this yesterday, but we didn't get to it. The air that we're breathing is all at the same what? Temperature. Whether it's oxygen molecules in the air, whether it's nitrogen molecules in the air, whether it's water molecules in the air, they're all at the same temperature. Which one is heavier, oxygen or nitrogen on the periodic table? Okay, I got two different answers.
Well, there's only two different options.
Well, that's good. So we didn't go with a third and say they were tied. Which one is heavier, nitrogen or oxygen? Oxygen. So in the air, what does that tell you about the speed of the oxygen molecules compared to the speed of the nitrogen molecules? Why?
It's harder to move. It's heavier.
There's more mass.
There's more mass. Now, those things may be all true, but you're getting into more than we need to. To be at the same temperature, a lighter object needs to move faster. To be at a heavier object, it needs to move slower to have the same kinetic energy. Okay? Rocio and I run a race. We finish with the same kinetic energy. Who wins? Rocio. Now be careful how you answer this. Why does she win? Careful.
She has less mass. She needs
What?
to go.
Why does she have more velocity?
Because small mass means you have to have more.
Okay, thank you. Nicely put. You didn't say, Mr. Brand, you have way too much mass. But I do have more mass than Rocio does. So if we end a race with the same kinetic energy, she's going to win. Okay? Same kinetic energy, she's going to win. We finish a race tied. Who has more kinetic energy? Why?
Because you got more.
Okay, and kinetic energy depends on mass and
Velocity.
velocity. If we finish a race tied, what does that mean?
Same velocity.
We're moving at the same speed or the same velocity. So now the only difference that affects kinetic energy is mass. Okay? So those three things interact. All right. So heat, temperature, and KMT. If you increase the temperature, particles have to move faster according to KMT. That is the only way you can increase the temperature in a substance. You cannot make the particles heavier. So the only way to increase temperature is to increase kinetic energy. And the only way to increase kinetic energy is to make the particles move faster, according to KMT. You cannot change the mass of the particles. Okay? Heat must also increase. Why would heat increase if temperature increases? Well, what's heat?
The sum of
The sum of kinetic energy. So this tabletop, I heat it up. I increase its temperature. The particles move faster, correct? How many particles are in it now versus when I heat it up? The same. But the particles are moving faster, right? So what has to happen to the amount of heat? Has to go up. If you increase the temperature of something, you are also going to increase the heat of something. You can't not. Unless you're somehow taking particles away, which we can't do. Okay? So when you heat something up, the temperature increases, so does the heat. Each particle's energy increases. That's why the heat goes up, though. Here, the temperature goes up because the particles are moving how? Faster. Not because the particles are getting heavier, but because the particles are getting faster. The heat also goes up, though, because the particles are moving faster, and heat is the sum of kinetic energy. Your kinetic energy goes up, your heat has to go up. That is a direct relationship, ladies and gentlemen. If temperature goes up, if particle energy goes up, heat increases. Direct relationship. If temperature decreases, the only way it'll decrease is if the particles are moving slower. If the particles are moving slower. This is according to KMT. This is that idea that all matter is made up of tiny particles and they are always moving. The only way you can decrease temperature is to slow particles down. Now, how do you decrease temperature? You take away heat. Remember, we can't add cold, but we could take away heat. Okay? So, again, you cannot change the mass of the particles, so the only thing you can do is make them move slower. So this also means that heat is going to decrease. Same amount of material there, but now the particles are moving slower. Your heat will decrease. Each particle's energy decreases, the total amount of heat decreases. Again, that is a direct relationship. So if the particles are moving slower, they have less energy. If they have less energy, you have less heat. Questions? All right. Take a minute and answer these next two questions, ladies and gentlemen. Actually, do slide 39 and slide 40. You can work with the partner next to you. You can work on your own, but let's go answer these two questions, ladies and gentlemen, on slide 39 and slide 40, and then we'll see what you got in a moment. Leaf, remind us again, what does kinetic energy depend on? And, okay. So right now we're going a little bit deeper than just saying kinetic energy. What does it depend on? It depends on mass and velocity. So understand, if you want to change kinetic energy, you need to change one of those two things. Najma, what does potential energy depend on? Three things. One of which you cannot change, but give me all three things if you can. Okay, mass, gravity, and height. Which of those three, Cynthia, can we not change? Mass, gravity, or height? Gravity. Okay? Gravity we cannot change because we are on Earth. We experience the same amount of gravity no matter what. Okay? We can, however, change the height of an object. We can, however, change the mass of an object. Therefore, we can change its potential energy. Okay? Brenda, Jacqueline, can one of you tell me, what are the things that heat depends on? What does heat depend on? From the last slide that we had, what does heat depend on?
How fast the molecules are moving.
Okay, which is the what? You're absolutely correct. How fast the molecules are moving, but there's another term for that. The what of them? Can you help her out, Brenda? How fast the particles are moving on average? It is part of KMT. Who can help them out? How fast the particles are moving on average? That's their what? Okay, it is their speed, but it's part of their kinetic energy. So you're right, kinetic energy or temperature, how fast they are moving. Good. What else does heat depend on, though, Brenda? Besides how fast or the temperature or the average kinetic energy of the particles, it also depends on what? Remember the definition for heat? The sum of kinetic energy. Okay, but also the what? Not sure? Okay. Well, if you sum something up, it means you're doing what? Adding it, right? Okay. So, in terms of heat, it depends on how hot the particles are, their kinetic energy, or how fast they're moving. We could say any one of those, okay? And it also depends on what? How many particles are there? So, we have something that's at a very cold temperature. Very cold temperature. So that means it does not have a lot of what? If it's very cold, it doesn't have a lot of what? Doesn't have a lot of temperature, a lot of kinetic energy. It could have a lot of heat. How?
It's very big.
If it's a very big object. Because even if you only have a little bit of energy, if you have a lot of them, you're still going to have a lot of heat there. Okay? So on average, how much do you think the average student at East has on them in a day? How much money do you think the average student at East carries with them?
Like cash.
Cash. $5?
$5.
$5?
Yeah, 5. Maybe.
Okay. $5, not a lot of money, is it? How about 6,000?
It's more compared to $5.
You're right. So what is 6,000 for East High?
The total number of money that each student would carry.
That'd be the total amount of money that all the students at East High would have on a daily basis. Why? Because we're adding up the individual amount each person has. If we say each person has about $5 and there are about 1,200 students at East, that makes it $6,000. That is a large amount, even though each person doesn't have a lot of money, correct? Same idea there. The object doesn't have a lot of heat, has a low temperature, but because of all of the particles involved in the object, it can still contain a large amount of heat because we're summing them up, we're adding them together. Okay? So, the example, the picture up there, an iceberg. Icebergs. Temperature is below 32 degrees Celsius. Or below 0 degrees Celsius, sorry. Why? Because it's frozen, right? Each particle is not moving very fast. But look at the size of this thing. There's a lot of particles there. So that means that there's going to be a lot of heat. Okay? All right, how is it possible for a small object to contain a large amount of heat? Well, if we're talking about a small object, what does that really mean? A little bit of what? A little bit of mass. So how can an object with a little bit of mass still have a lot of heat? What would it have to be? What do you think, Christian? Little object to have a lot of heat, what does it have to be?
Big mass.
Yeah, but it can't be. It's a little object.
Oh, that's moving part.
Has to have fast-moving particles. If you have fast-moving particles, that means your what is very high? Your temperature and your kinetic energy, both of them, right? They're all related. So, if you have something like lava, lava has temperatures of basically 1200 to 2000 degrees Fahrenheit, 700 to 1200 degrees Celsius. A little bit of lava would contain a lot of heat. Why? Because it's very hot. Not because of the mass, but because of how hot it is. Okay? So you can have a lot of heat either by having a very big object at cold temperature or a small object at a very high temperature. Either one. Okay? All right. The second slide. If two substances are at the same temperature, explain how these substances could have particles be at different speeds. So they're at the same temperature. What does that mean? Rocio, what does that mean if two things are at the same temperature? That they have the same what? Not necessarily. They do have to have the same though. Nope, not necessarily. You've hit the two things that affect this one thing though. To be at the same temperature, they have to have the same kinetic energy. Now, kinetic energy depends on mass and speed, correct? Mass and velocity. So two objects are at the same kinetic energy. How can their substances have particles at different speeds? If their masses are different. So this picture up on the top here, ladies and gentlemen, you've got these two large objects and a bunch of these small ones. What do we know about the small ones if they have the same kinetic energy as these large ones? They've got to be what? They do have to be the same temperature. But how can they be the same temperature if they don't have the same mass? The smaller ones have to be what? Moving faster again. Smaller ones have to be moving faster. The larger ones have to be moving slower. They can have the same kinetic energy. They get it different ways. One gets it from being a large object moving very slow. One gets it from a smaller object being very fast. Okay? How is it possible for frozen ice cream to have the same heat as boiling water? What?
The ice cream is really big.
Yeah. You have a lot of ice cream and how much water? A little bit of water. Remember, heat, we sum up all of the energy. Heat, we sum up all of the energy. Ice cream and boiling water cannot be at the same temperature. They cannot. What would happen to ice cream if it was at 100 degrees Celsius? It would melt. It would probably even start to boil somewhat. So they cannot be at the same temperature, but they can have the same heat. Big bowl of ice cream, little bowl of water. Okay? Of boiling water. Can be there. All right? Questions? Okay, now what causes something to go from being a solid to a liquid to a gas? Heat. Heat. What happens when you add heat to a liquid? Does it turn into a gas? So if I take this bottle, can I borrow this?
Mm-hmm.
If I take this liquid in here and I start heating it up, it's going to turn into a gas right away?
Start boiling.
Not right away. What will happen right away? No.
Or no, the particles.
What temp is this at? Bad example, by the way. That's not plain water. Plain water in here, what temperature is this at? Which is 20 degrees Celsius. 69 Fahrenheit. 20 degrees Celsius. If I add energy to this, is it going to start boiling right away? Not until it gets to what? Well, what is going to happen as soon as I start adding energy? Temperature is going to start going up. Okay? So it's a common mistake that people say, well, if you heat something up, it starts to boil if it's a liquid. No, it doesn't. It just heats up. Now, if you add enough heat, it will boil. And heat does make something go from a solid to a liquid to a gas. But not right away. You have to get it to a certain temperature. Okay? You have to get it to a certain temperature. What you're looking at on the board here, ladies and gentlemen, is the heating curve for 1 mole of a pure substance. Okay? By the way, titles are important, ladies and gentlemen. Okay? What's on the x-axis? Energy. What is energy? Okay, but that's the unit. But what is energy? What is the most common form of energy? Heat. So we're talking about doing what with heat here? Adding it, increasing it, putting it in there, right? Okay, what's on the y-axis? Temperature. Okay? Temperature. Now, another way of saying that is the what?
Oh,
Kinetic energy. Either one. Good with both. Up at the top is our title. Take a look at your title. Heating curve of 1 mole of a pure substance. Pure substance just means it's only one thing. Iron, gold, silver, salt, water, sugar. One thing. Can everything melt? No. This desk is made of wood. Wood will not melt. Okay? Can that iron pipe on the wall melt?
Yes.
Can it boil? Yes. Many things can go through the 3 states of matter, not all. If you can go through the 3 states of matter, ladies and gentlemen, this is what it looks like when you go through there if you were to graph it. How do we get that pipe to melt? We add energy, we add heat, just like we're doing here. So that pipe, for a while, will be a solid, even when you're adding heat, until you get to the point where it will start to melt. So what state of matter is A down here, ladies and gentlemen? A is when it's a solid. At its lowest temperatures, things start out as a solid. So what's happening at B here? Suddenly it was a solid that was heating up and then it levels off. What's going on? It's melting. It's melting, or it's going through a phase change. Either one, melting, fusion, either one, you can use either one of the terms. After something is melted, what does it become? So what is it over here as C? A liquid. Now, all this while, what am I doing? To get from here all the way to here, what am I doing? I'm increasing energy. I'm adding energy. And what is happening because I am adding energy? I'm adding heat. The temperature is going up. That's why the line goes up, correct? What's not happening here? Temperature's not going up, is it? Temperature's not going up. Here it's going up though, right? In C, it's a liquid. Why does the temperature level off again? It's going through another phase change. It's turning to a gas. What do we call that one? Nope, not evaporation. We wouldn't have to add any heat for that to happen. What's it called? Water on a stove.
Oh, boiling.
Boiling or vaporization. Either one. I'll take either one. Hey, by the way, I have freezing here and I have condensation here only because we could also look at this going the other way, right? If we were going this way, this is melting. If we're coming backwards, it's what? Freezing. Okay, so I'm trying not to confuse you here, but that's why these terms are here, okay? So then what happens after it boils? Here.
It's a gas and the temperature is increasing.
Thank you. It's a gas and temperature is increasing. It is a gas and temperature is increasing. Now, the only times that temperature increases when you add energy is when your matter is in what? Nope, actually just the opposite.
When it's already phased.
When it's either a solid, a liquid, or a gas. During a phase change, what happens to your temperature? Stays constant. Okay? So let me ask you this. We're adding energy as it's a liquid, correct? Where's the energy go? What does it cause to happen in the matter? Think in terms of the particles. What happens to the particles if we are adding energy to a liquid? They move faster, which is why their temperature goes up, correct? Okay, at the plateaus, are the particles speeding up? So where's the energy going? Law of conservation of energy says energy has to go somewhere. Where does it go here? Goes to making the particles move faster. Physically move faster. Energy says you're gonna vibrate, you're gonna move around quicker than you were before. Where does it go here? Nope. Because it's going into the matter, right? But the temperature isn't increasing. It's got to go somewhere. Any idea where it goes?
Changing the phase.
Goes into changing the phase. Specifically, the particles in your desk are held tightly together, correct? So tightly you can't even put your finger through them, can you? Okay? Well, not normally. I mean, if you break the desk, maybe you can. But you cannot put your finger through, right? They're held really close together. How are the particles in a liquid? Are they held close together?
Not as close to the solid.
No. Can you put your finger in?
Yeah.
Will they move out of the way?
Yeah.
Yeah. Can you put your hand through a gas?
Yeah.
Will the particles move out of the way?
Yeah.
Yeah. So in a solid, there is something called forces of attraction. Holds the particles together. Can you give me an example of a force of attraction? Magnetism. There is a force that holds this magnet to the wall here. Now, just as we talked about the other day, I think it was with you guys, maybe it was with my chemistry class. Is this magnet still attracted to that metal? Yeah, that never shuts off, does it? But if I drop this, what's going to happen? If I let it go, let me rephrase this, what's going to happen? It's going to fall, gravity is going to take over what? Strongest force wins. Now, the only way this is coming off of here is if I put a what into it? Oh.
Stronger magnet?
Nope. Stronger force. What's the stronger force? Me. I'm pulling it away from the metal. Stronger force. Okay? Stronger force always wins. I'm the stronger force. Magnetism wants to hold it in place. I put more force in. I pull on it. Force is a push or a pull. I can take it off. Okay? Now that doesn't mean the magnetism still doesn't exist. But I had to put some energy in to pull it off the wall, right? Same thing here. You're putting energy into the matter to get it to go from being a solid to a liquid. Then you're putting energy in to get it to go from being a liquid to a gas. By the way, I don't care what the substance is. All substances, their heating curves have these 5 regions in them if they go through the 3 states of matter. If they go through the 3 states of matter, every heating curve will look like this. Every one. Okay? Every one, it will look like this. Now, what will change? How much energy you have to add. How steep the lines are. How long the plateaus are. At what point the plateaus are. But the shape will always be the same. Always. What phase change is happening here at B? And freezing. So if we go over to the y-axis, what can we find? What do we call the temperature when it will melt or freeze? Or, which means they are the what here? They're the same. Freezes and melts at the same temperature. Question is, are you going from a solid to a liquid? Adding energy? You're going from a liquid to a gas and doing what? Taking it away. Same thing up here. What phase change? And condensation. If we follow it across to the y-axis, what do we get?
Boiling point for
The temperature which that change will occur, also known as the boiling point and the freezing point, right?
boiling point, condensing point.
I'm sorry, boiling point and condensing point. Thank you. Sorry. Okay? All that from this graph, ladies and gentlemen. All that from this graph. Okay? What is constantly being added in this diagram? Energy. Energy is constantly being added. Why are the lines going up in the three segments? Why in A, C, and E are the lines going up?
Because the temperature is.
Sure, no, because you're adding energy.
Okay, I agree with you, but we are adding energy in B and D. Line's not going up.
Oh, well, yeah.
Temperature is
Temperature is increasing, or because what else is increasing? Kinetic energy. Which means what is increasing as well? Okay, and the speed of the particles. All of those things are increasing. Temperature is rising, kinetic energy is rising, speed of the particles is rising. Heat is rising. More energy put into it. Okay? What's happening to the particles of matter in A, C, and E? It's actually happening to the particles. They're speeding up. They're speeding up. They're moving faster. They're moving faster. All right. That is where we're going to stop today, ladies and gentlemen. Okay? That is where we are going to stop today. So, again, as always, I don't know if you have anything on it or not that could help you, but if you want to take out your periodic tables before today's test, please feel free to do so. Miro, can you please put away the phone? It's on the other
What
side
the
of your
heck?
computer.
It's right there. What the heck? Why is
Oh,
that?
hello?
What
Okay.
the heck?
Okay?
You know his rules.
So if
Did
you,
you do
Are we
it?
gonna need the
You're literally trying to cheat on the test.
I
Now.
literally.
cool your
Okay,
jets.
he's literally trying to cheat on the test.
Okay.
Only if I ask for
Because
it.
your phone is like literally out.
It's not
It's
on the
literally
table.
out there.
I literally
But
can't
it's
see it. I
literally out.
literally can't
It's
even reach
literally
it.
out there. You're
I
basically
can't
cheating.
even reach it.
You're basically cheating.
Are you children right here?
It's not my fault. It's his.
No, it's his fault. Yep, you're a guy now.
Do you know what Mr. Bus called me Bryce the
This
other
is-
day?
this is
He
why
called me
you
Bryce, like
guys were
genuinely.
adopted, so I can get
I thought my name was Bryce.
Okay. All right, ladies and gentlemen, the quiz is on the computer. I will put it into the Google Classroom site, and you can get working on it, ladies and gentlemen. No, it's not out already. Give me a minute. It is now in Google Classroom. It is now at the top of Unit 2 Matter, ladies and gentlemen, and it is now ready for you to go ahead and begin taking.
It just started. It's 5 days in.
It's not my bad.
The good news is you only have 361 more days to go.
361 days of failing. Every
And the
semester.
best part is, just for you, there's an extra day this year.
Another extra day
What?
Another
What?
extra day I have to
Why?
see you.
I don't know.
Yeah, actually, no. Means you get out a day earlier, because we only have 100 and so many days of school either way. So,
Oh, is it leap year?
just because there's an extra day next year doesn't mean you get to see me an extra day.
Congratulations, everyone who's born on the leap year.
What?
5 years old now.
Nothing, I forgot.
Go to work!
Everyone. Hey, we were going.
But I wasn't born on that day. What? That's your problem. That's not how it works. Mr. Graham, you want full sentences?
No, because even at the start I say to please be as brief as possible.
Oh, yeah.
So if you can do it as long as you can do it in a few words, do it in as few words as possible. Okay? Go to work, go to work, go to work. Well, then take the 0 and make it easy for me to grade.
Okay. I'm gonna do it. I'm gonna do it right now.
I have a question already.
Oh my god. How do you want me to describe it? Like.
So the shape of a constant and an inverse, we gave you exactly what a constant looks like and exactly what an inverse.
So we just put that in.
Yep, you just put that in there. So the graph is doing this and this.
Alright.
That was what we did that whole first start of this unit.
Did we have to put this also?
Okay.
If it's none of these other.
Well, you can't select one and none of the other answers.
Okay, so it's just that.
Yes.
Okay.
So,
Wait.
by the way, the ones where it's a square box and it says select all of the correct choices, there could be 1, there could be 2, there could be 5. You have to pick all of the ones that would be correct. If none of the other choices is a choice, do not pick it and another choice because that cannot be right. So if you're saying none of the other choices, you shouldn't select any of the above.
Oh, for this one.
For the ones where there's a square box where it is the select all that are correct section. There is a section where it is just multiple choice too.
Am I supposed to figure something out, or is this right? Just that? We're supposed to read it, or?
Well, I would look at everything over and then decide what's constant and then write it
Well,
down.
it says right there, Mom.
And where are we at?
What if it's asking?
Well, I can't tell you what the correct answer is.
Well,
It's-
yeah, but.
It's gonna be multiple.
No, it doesn't.
What's that?
You just click all that at once.
So if it's a
Why would
square
you put
box,
multiple?
you-
Why do
there
you
might be more
Why
than
do you
one.
do this?
Because I want to see if you actually know this.
I don't like that you do this.
I know, it's terrible. So,
I don't
but if there's
know.
more than one correct answer, click it.
I don't know if there is though.
Well, then click the one you think it is and go with it. That's all you can ever do. I understand it by the first 5 times that you've said it.